Can we mic you up?
Yeah, it is very much. Pretty much ready to go?
Yeah.
Okay, I'll. Okay. So there's an 8 dimension, like,
Yeah.
in exactly, in any state that I did. You can do anything you want.
What year?
Sorry.
Thank you.
Okay. Refocus. Introduce Ehud Altman, who's a professor at UC Berkeley, and he'll be telling us, I think, some more things about measurements and decoherence. Maybe both together.
Thanks. Really happy to lecture here. Last time I did that was virtual in the pandemic, so it's great to be here in person. Let me finish writing this. Coherence, induced transitions. In topological. I am. I think it's on. Maybe it's not. Yeah, it's just not close enough. Can you hear me? Okay. Okay. So my just quickly the plan of my lectures. I tried to write big. Someone asked me, and so hopefully I'm not going to make a mess with. Usually when I try to write big, it doesn't work very well. So I'll start with measurement-induced phenomena, and I think I'll tie in pretty well to what Roman talked about in his last lectures, and maybe I'll even give you some exercise to apply what you learn. But I'll try to give it from a slightly different angle of the quantum of looking at the circuit or the state we're measuring as a channel for quantum information transmission, and see how we understand the non-local effect of measurement through that. And then I'll basically back up a little bit and go to an even simpler setting than a dynamical quantum circuit, and just ask the question, if I have a quantum state, for example, a quantum ground state, and I do some measurements on it, how do measurements impact the quantum state? All of this is under this new kind of way of thinking about experiments in physics, which is very different, I think, from traditional experiments, in the sense that in traditional experiments, measurements are only serving as diagnostics. So you have some pristine state, you're measuring it by doing, say, for example, a neutron scattering experiment. And the measurements are not supposed to change the system. They're basically, if you're doing it right, you're doing linear response, you're actually using the measurements to measure some either static or dynamic correlation functions of that are intrinsic to your system. On the other hand, we know that measurements in quantum mechanics have kind of a special role, and they can cause a collapse of the wave function, and that collapse could be highly non-local, and I'll talk about it later. And new kinds of experiments which allow, for example, mid-circuit measurements or monitored system that the monitoring does not completely destroy the system, have the measurements have this new role of not only diagnostics, but also as an active role of preparing a state that you then want to diagnose. And so the upside is that this can lead to, because the effect of measurement is very non-local, it can lead to very interesting and novel collective phenomena that I want to discuss, and I'll discuss them in this first part of the lecture. Even in the simple case when you're not dynamical, you're just measuring a single state. But on the other hand, there is a downside that when we're measuring system, we get, when we're preparing the system using the measurements, we're getting a state only once. Because if we repeat the experiment, we're bound to get a different state because we get different measurement outcomes. So how can we diagnose a state that we basically get only once? And that's at the heart of why these effects are so hard to observe. It's what is called the post-selection problem. And in lecture 2, I'll devote probably most of the lecture to the post-selection problem and various ways of trying to overcome it. I wouldn't say overcoming it because there is no perfect way to overcome it, and probably there will never be. It's probably fundamental, but I think there are very interesting ideas of how to gain information on the post-measurement states without gain some information, although not everything we want without post-selection. So because my lecture series is called Measurements and Decoherence, the last lecture will be devoted to decoherence. It'll change gears a little bit, but we'll use a lot of the at least conceptual machinery and quantum information objects that I'll define in the first lecture to understand decoherence-induced transitions in topologically ordered states. And here I'll maybe preview a little bit things you'll get in the third week on topological codes and error thresholds in topological codes. I'll give you a very kind of an orthogonal, or I would say literally dual picture of these error thresholds, but in some sense, it gives a more general view of them that can be applied not only to topological codes, but to many other topological states that are not necessarily stabilizer codes. Okay, so let me start with today's lecture 1. And just give you the simplest example where measurements really have a very non-local effect due to quantum collapse. So probably Roman talked about it already. So if I start from some state psi naught, and then I measure it in some basis. If it's projective measurement, it's the simplest example. Then I have a set of measurement operators which correspond to projections on the different possible outcomes of, let's say, the measurement operator is some, say, Z, a Pauli Z operator, and M is plus minus 1. These are projections on, say, the upstate and downstate of the Z operator. So then the state I get after, let's say there's different qubits and I'm measuring a particular qubit I, then the state I'll get after after is psi M. Acting on the state over square root of M. Generally, we probably don't need the square in this case because it's a projector, but we'll put it. And in principle, I could also include the situation where I don't measure, and then I add, there is no measurement, and I'll add M equals 0. So M, this would be M plus minus, and M0 would be, then I'll have to add a probability here, square root of P and square root of 1 minus P doing nothing. That is another example of a measurement channel where I also have a probability of not measuring. And the probability of not measuring in this case is 1 minus P. In any case, I think Roman talked about this set of measurement operators form what is called the POVM. Yes? Oh, yeah, in this, yeah, so I'm imagining a state that is defined on some sites, I, and let's say I'm measuring only site I. Right, just as an example here, okay? Okay, so this is just to set up what we mean by measurements, at least in the simple case of projective measurements. And if we just measure and I don't say probability of not measuring, I can forget about these probabilities. These are just projections then. Oh, and this is just the probability of a particular outcome is given by the expectation value of m squared. Okay, so okay, so now let's see that measurements can have a non-local effect. And let me give you two simple examples. One simple example is if this state is just made of 2 qubits and they're entangled in a maximally entangled state. For example, this is A and B, and A and B are entangled, so it's basically up, up, plus down, down to normalization. So this maximally entangled state, and now let's measure A. After I measure A, I will collapse the state into, if I measure up, I'll collapse the state into this. If I measure down, I'll collapse it into this. So after measurement, if I measure A, and I'll collapse it to just, so basically if I, pictorially, it will just be this state. So there used to be some quantum correlation between these two parties that now, after doing the measurement, is collapsed, is eliminated. Okay, so measurements can destroy quantum correlations, but I want to show that measurements can also create new quantum correlations. So here is another example. Let's say I have 3 parties, and they can be very far away from each other. So for example, I can have a party M here, party A and a party B. Let me call that party AR for reasons I want. And the party B, and again, the same way, M could be somewhere in the Midwest, R is here, and B is in the East Coast. And we have a situation where we started out with a bell pair, maximally entangled state between a qubit held by this M party and by us here at R, and another qubit is shared, another bell pair is shared between M and B. And now let's measure, M now measures in the bell basis. So it does a two-particle measurement in the bell basis. And what happens is basically, well, depending on the measurement outcome, now you'll get this situation where depending on what comes out of the measurement here, you'll get still a bell pair, but one of the other possible, 4 possible bell pairs of 2 particles that depend on what they measured here. In this case, you see that by measuring, M created a 2-particle correlation that didn't exist beforehand. So you created a new measurement. And sometimes people say that, this is the basic protocol for teleportation. And the idea about it, okay, so let me talk about this a little bit more. Well, okay, so before that, I want to, before talking about teleportation, I want to kind of define a quantum information object. How do we know that we've created? So here we can see, because it's a simple situation, we can see that we created a new correlation, a new quantum correlation. Is there object that will allow us to quantify a non-local correlation, quantum correlation that is created in a particular process? So for that, I want to define an object called a coherent information. And soon we'll apply it to this situation of measuring these two qubits. So let's say I have a quantum channel. So maybe someone defined the quantum channel for you already. I'll kind of quickly say what it is. So now I have an input A, I have an output B, and in quantum information language, A is Alice, B is Bob, and for some reason they always use these names, and E will be the environment in this case. It's not Eve in this case. We'll get to Eve later. Okay, so what do I mean by a quantum channel here? This is N over O. Well, the quantum channel is actually if I neglect the environment and I input a state rho into this device, and I get an output here, this is, and it's not necessarily unitary. However, I can purify it by I can always purify it to make it a quantum channel. It means I can always purify it by enlarging the system and including the environment that it decohered with, in which case it's just a unitary process on the entire system of our input output, which is some unitary here and some unitary acting between the system and the environment. And if I didn't look at the environment, this would be called a quantum channel. Now that I'm allowing to have the environment, it's a purified system. And now I can ask the question through this quantum channel, through this quantum device, if I send some information from A to B, how much quantum information passes through this channel? And this is quantified in quantum information by an important object called coherent information from A to B. Let me first define it and then understand its properties and why it does what we want it. It's basically S of B minus S of AB. Now, I want to stop a minute. Probably you've seen this many times, but there is, in quantum information, if I have an input A, which is some state, I can always kind of deform it to basically have add another qubit to the system, like this qubit, and say I'm maximally entangling that qubit to here and to this qubit. And in this case, I can look at the entire process as a single quantum state instead of a process. So now instead of a unitary process, I basically have a quantum state that includes the party A, the party B, and the party E. So the state I wrote down here, and we'll write it soon, we can also write in this way. Okay, so we'll write it soon in this way. And if you think about it classically, this is kind of obviously a negative quantity, right? If we think about it classically, because this is the entropy of some part of my state B. This is a state that has three subsystems, A, B, and E. And classically, if I look at the entropy of a subsystem and the entropy of a larger system, the entropy of the larger system is always larger than the subsystem. So this will be always negative. But in what?
Well, unless B becomes so small that
classically, in a classical world, right? So in a quantum system, it doesn't have to be that way because, for example, if A and B are entangled, right, there is information that we gain. And so if this S, the entropy quantifies the information we don't have, once we encompass the entire system, we already have certainty, and this entropy can be even zero, right? So quantum mechanically, this doesn't have to be negative, of course. and if it's not negative, it actually implies that there is some quantum correlation between A and B. So already you see why this quantifies the quantum correlations between A and B if this is positive and not negative. Negative, it could also be in classically, and I'll talk about it a bit more.
You repeat the part that it is the A as a subsystem. I didn't follow it.
Oh, why A is a subsystem? So this is called a Choi map. If you have a unitary from some input A to output B, I can always think of the unitary operator also as a state. So you can think of, if this is an input and this is an output, this is just a tensor. I can think of this tensor also as representing, I can just think of this tensor as representing a state where this is a party A and this is a party B. So every quantum state is basically a tensor. It's a tensor that has many indices, and the overlap with a particular basis state is when I sandwich or if I project this index onto a particular state, product state, for example, if it's a product state basis, let's say alpha, project it into alpha here, alpha and beta here, that would be the state psi alpha beta, right? And I could do the same for this unitary operator. I can sandwich a bra here and the cat here, and it will basically be like a state. So basically this map, I can, instead of thinking of it as a unitary process from A to B, I can think about it as a state in a larger Hilbert space. Yes?
What you're saying is the same thing as just saying, you know, you have an A unitary, you have B.
Yeah.
Versus how A and B in this one is like a tensor product. Like in the top left, where it's like that.
This is not tensor product because there is still, the state could be non-trivial. There is still a unitary here. For example, unitary could be swap, for example, or sorry, it's one site unitary in this case, but yeah.
It looks like there's a state A and there's a state B.
There is no there is just one state. The A and B are just degrees of freedom. There is no state here. So the state now is just the entire thing in this case.
Can you write this in terms of like, maybe I'm the only one confused. Can you write it in terms of like,
yeah. So you, okay, you, right. So the matrix elements of a, so if I have a quantum state, psi alpha beta, that means this. Okay, so psi alpha beta is if I have a tensor like this. This is a tensor with two legs. Psi alpha beta is when I sandwich this tensor with a product state alpha beta. Okay, and U alpha beta is when I sandwich U with alpha beta. And I can call that, I can also call that the state in a larger Hilbert space.
Meaning you're interpreting the matrix.
I'm interpreting the matrix element as an amplitudes, yeah, as a wave function. That's right. So I can always interpret this as a wave function in a larger dimensional Hilbert space. So a similar thing is if I have a density matrix, just as an, that's a very useful. And so if I have a density matrix rho, it's basically some sum over alpha beta. So again, Ket-Bra notation is have some rho alpha beta, right? Alpha beta, and that's it's the density operator. It's an operator. I can think about it as a state in a higher Hilbert space by kind of mapping all the bra to a ket. Yeah, turn the bra into a ket. That's right. And that will turn it into a state in a higher dimensional Hilbert space. Right. So I can now rewrite this as rho, say, ket like this, which is just sum over alpha beta, rho alpha beta, alpha. Although I need to star some. Yeah. So this will evolve by U dagger, by U star now instead of U dagger, right? So if I want to evolve this, right? So U dagger rho U will go to U dagger will go to U cross U star, because I basically turned ket into bra. I have to transpose U, and I have U star acting on now rho, this rho. Okay, so this is this operator state correspondence.
Well, here, that one is a state. You call it an operator, it's really a state.
Yeah, but it's a state in it. Well, okay, but it's a state in the doubled Hilbert space. So the double, but it is exactly the same. So this time evolution is also operator, but you can think of it as a state in a doubled. Any operator, you can do this and think of it as a state in a doubled Hilbert space. Psi alpha beta, no, is a state. So I think of it as a state in a two-dimensional, or sorry, a two-qubit Hilbert space, for example. If it's a state in a two-qubit Hilbert space, so psi is a state, and then I look at the matrix at the amplitudes, in particular product state basis functions. I'll say it's psi alpha beta, and I'll draw it like this. Now I can look at the density matrix, which has alpha and beta on, up and down, corresponding to ket and bra, but I can think of it as a ket in a larger dimensional Hilbert space. So similarly, I can think of this unitary process also as a ket in a higher dimensional Hilbert space. And by doing this, you see that essentially it's like taking and maximally entangling, because when I have this line connecting to two qubits, it's basically I'm summing over all the possible states here, alpha, alpha. So I'm inserting the state I'm inserting into. So now you can think about it again as an operator. If I draw a line here where this is the input and this is the output now, but now what I insert into here is a bell pair, is a maximally entangled state. So from, I should draw it like this, alpha alpha inserted into now something that is here, it's just a unit matrix, a unit operator times U. So this is what is drawn here, and this is giving me a state. Sorry, I should write it like this, because this is input, alpha alpha, and this is the new state I get, and this is the state I get here. I didn't draw the rest. If I want to include the environment qubit, I'll have to add something like, let's say it starts with a 0 here, and then I have to include also a unitary that connects B and E, and the state I drew here is basically just this.
You can do this, but like, suppose you now want to use this new way of looking at it.
Yeah.
Let's say you want to evolve a state forward.
Yeah, I'm going to do it soon. No, so I'm going to evolve. So I'm going to do it. For example, I would like to evolve the density matrix soon. And when I evolve the density matrix, right, I'll evolve it by, I'd like to evolve kind of a density matrix that looks like a state. So I'll evolve it with two copies of U, one U and one U star. But here there is nothing. I didn't evolve or anything. I just want to represent the state.
Like I take that state AB.
Oh.
And I wanted to add can I add a 2-qubit unitary that now acts on
Yeah,
on A.
yeah,
we'll
if
find star, and then
yeah,
on B,
here it depends on, right, the physical situation. If the physical situation is really that it's a process and not a state, then you'd have to convert the Heisenberg evolution into some kind of evolution only forward in time, but then evolved with U star instead of the U dagger. Yeah. So it depends what really you want to do. Yeah. Yeah. So yeah, that's right. So for this, it's just very convenient to think about it as having another qubit, usually called the reference qubit, because it really, you have to remember, it corresponds to the initial state in the physical picture. But because it's a state, it could be, in principle, I could also think about it in this situation. It's going to be a real state like this. There is a real state of three parties. So first, I want to give the usual coherent information definition in quantum information, and then I want to apply it to this particular case. And after applying to this particular simple case where it's very intuitive, I want to apply it to the measurement-induced transition, and you'll see that it's actually the same thing. And after that, we'll use Romann's mapping to StatMech model to see how this object and other information theoretic objects look in the StatMech model, because they have a very intuitive kind of translation to that model. So that's the plan for now. Okay, so I was I gave you the basic definition for one very simple property that you can prove easily. I'll let you prove it at home because I've gone a bit far, but it's easy. So that coherent information I see from A to B, what's the largest value it can get? The largest, anyone has feeling what's the largest value it can get here? So these are both positive quantities. It's probably the biggest if SAB is completely zero, if it's a pure state. It's basically you're decoupled from the environment, and then SAB is a pure state, and then it's basically either SB or SA. They're the same. So let me write SA, because that makes it here. Now you understand that this coherent, if everything is perfect, the environment didn't take anything, then the information that B has is basically what the maximal information that the input had already. So basically all the information goes through. On the other hand, the smallest, what's the smallest it can get? Smallest it can get is actually if all the information about A goes to the environment. So if the environment and A become a pure state, right? In this case, you'll get, then this is going to be equal to SA, and this is going to be a pure state by itself, 0. So you'll get minus SA. So this is not a proof, but it's very compelling argument why it is between SA and so in a sense, if this is the maximum, it does mean that all the information came in. What does it mean that it can become negative? Well, to understand, remember that if we're in a classical system, we can only get negative values. So actually getting 0, for example, doesn't mean we don't have any information in B. It means we have some information, only it could be classical. So just, I know I'm going very slow, but let me also make this small digression and say what it relates to in kind of Shannon theory of classical information, because I think it's kind of useful. So in Shannon theory, so let me use H for entropy, classical entropy. Okay, so if I have a situation where I have two parties A and B classically, and there is a notion called conditional information, HA, information I have on A, given that I know the value of B. okay? And this is given by, in Shannon theory, it's given by HAB minus HB. You see that it's very similar to this, except these are Shannon entropies instead of von Neumann entropies, and it's sort of flipped. What it means, it basically means what is the uncertainty I have on the random variable A if I somehow know, if I know the values of B, okay? What is the remaining uncertainty? When this is 0, I have 0 uncertainty on A. So if A and B are perfectly correlated, then if I measure A, I know what B is. So this would be 0 in this case. It tells me what is still the marginal uncertainty having, you know, known A. So now you see that basically the coherent information, if I want to kind of quantize this and just write the same thing for a quantum system, I'll write SAB is SAB minus SB, and that is equal to minus IC from A to B. So the coherent information is basically the negative of this coherent information. So you see that when this is, and clearly I cannot have negative uncertainty in the classical case, right? And the fact that I can get negative uncertainty, I'm in negative uncertainty about A, it means that there is some kind of quantum correlation. And it turns out that basically it quantifies the, and so we'll see that, quantifies the ability in principle of B to perfectly decode and know what the state, the quantum state of A is, which is basically to apply some unitary, and so that the state of A will perfectly show up in his apparatus, okay? So let's apply it now for, so this, let's write the effective circuit for this protocol that we had here. Let's write the circuit. So here is a circuit. The input is A, or R, I think I called it there. So the input is R. This is M, and this will be B. And now because M gives a classical measurement, I'm going to connect it. It's not, M doesn't hold a quantum state at the end of the process, right? It just holds classical measurements with probabilities PM. So I'm going to, so basically it's dephased completely, M, right? It has, with probability M, if you think about the whole process with all possible outcomes, we know that measurement is a quantum channel. It will give me in M density matrix which is diagonal in this measurement basis and has exact the probabilities. And I want to purify this density matrix. I need to connect it to some ancilla. Okay, so I need to connect it to an environment with some unitary. And you know, this can be done in principle in many ways, but there is a very neat way of doing it if I do it like this. So this is a control X, let me call it a CX gate. And a CX gate, this is what I call CX here. What is the CX gate doing? It takes, if it takes in, it always takes in a 0 of the environment and M of the system, and outputs, and you can show it's really unitary. It outputs M. Sure, sorry, yeah. So what this does is whatever is, so what this does is after this, the state of M, rho M, after this is just diagonal PM. In all this CX gate is written in the basis of measurement. And so these M's are the different possible measurement outcomes. In this situation, it's the Bell basis. And so if there is an input of the ancilla at some reference state, the ancilla has to be a four-dimensional Hilbert space in our situation. And this is what you get in this four-dimensional Hilbert space. Okay, so in this case, this is what you get. And the ancilla also has the same density matrix after, because they're basically becoming maximally entangled. Well, not maximally entangled. They're in a pure state together. Yeah. It's not every state. It's just in a particular set of states that, yeah, there is no, this is a completely legal gate. You can actually build this gate easily. Okay. Yes. Not single qubit. You need as many qubits as the Hilbert space dimension of M. Yeah, so in this case, the environment is not a single qubit. It's 2 qubits, right? You need the same Hilbert space dimension. Yeah, sorry. So, okay, so now I do that, and okay, so now we can calculate so what do we want to calculate? We want to know how much information Bob can get from Alice. Alice has, so let's do what is really happening in this teleportation, in actual teleportation, what is going in the usual scheme for teleportation. Actually, M and Alice are usually in the same room, okay? So the non-locality is between that room and Bob. So usually the teleportation process is we have state here. Alice has Alice shares a Bell pair with Bob. This is what we called M. And then inserts a state psi into here. Okay, so that's the usual teleportation picture. So this would be inserting a state, remember, is the same as in this Choi map, looking at the state with a reference qubit. And now I want to ask how much information about the state, how much of the quantum information can go to Bob. Okay, so I should write the coherent information from R to what? So this is the circuit. So what should I write here? Should I write R to B? If I write R to B, it's basically as if Bob has no information about the measurement outcomes, right? So nothing non-local can. I'm going to ask whether some non-local correlation is generated between R and B. And of course, no non-local correlation can be generated. Look at my circuit completely unitary. R and B are, R is in Colorado and B is in New York City. And what is going on here is completely local. So of course, I cannot generate any non-local information between R and B. So that must give me 0. There was no information before. There can't be information that is generated in this local circuit. Remember that this decoherence happens, this dephasing happens here in Colorado. So there can't be any non-local correlation. And indeed, that matches with the actual teleportation protocol. It's not enough. There is not magically information that can be passed to Bob. For Bob to get the information, he needs to know what Alice measured here, the measurement outcomes. So really, Alice has to send over some classical channel the measurement outcomes. And this can be described here that basically whether this combined system, now Bob has M in his hand too, not only B, right? So the combined system of B and M, whether now it contains enough information to reconstruct the state. So the state can only be reconstructed if I have, if I have what B has in his hand plus M. Yes.
But over here, I guess you don't know what little m is, but over here you, by measuring in Bell bases, were able to create.
Yeah, but I need, but for Bob to, I don't know what M is. If Bob wants to recreate the state, he needs to know what M is. So let me actually go to this. So so this is what I want. This is what I want. Let me now write explicitly what it is in terms of the measurement outcomes. Okay, so let's write it. So this is SMB minus SE. And another way to write it is SMB minus SM, because M and E have the same density matrix. So now now I can use this. So I can do something. I can make some progress, and the progress I can make is that I know what rho M is. I wrote it. It's just this diagonal, and I also know how rho MB looks like. So let's write rho MB. The combined density matrix of M and B is basically if the measurement outcome is M, which has a probability PM is M1, which has probability PM1, then I have one density matrix. Let's call it rho B of M1 for B. If I have probability if I have measurement outcome M2, I have B has a density matrix rho B M2, so it's block diagonal like this. Okay, so this is rho MB. Remember, M is completely classical. It's basically defining the probabilities of the different measurement outcomes. So this is the MB density matrix. Now I can compute this. IC of R to BM is trace PM, so sum over M. Now I can sum over blocks, right? So sum over blocks, trace PM rho BM log PM rho BM minus sum over M. This is the SB minus SM PM log PM. Okay, so now I can, well, now maybe you can already see that I can open this up. PM log PM will vanish, and I'll get sum over M PM rho BM trace, sorry, there is a trace rho BM log rho BM. Which is just nothing else but sum over M PM SM SBM, which is kind of nice. So now we see that the coherent information that we can you see over there? It's a little bit sharp angle, wide angle. So this is just the average over the measurement outcomes of the entropy that B has. So and in this case, it's very easy to calculate, because for every measurement outcome, no matter what, I'm in one of the Bell pairs, and this entropy is the same. So this average is just, and the probabilities are all equal probabilities. So the average is just log 2. So I have the full log 2 entropy, and it means that I can teleport the entire, Alice can teleport the entire state in this situation. Yes.
So that's like a generalization where here you measure a little m.
Yeah.
And you tell Bob about it.
Right.
And
That's
then
right.
there's a complete table.
Right.
But here, the probability of measuring particular value.
Right. Right. That's right. And average over that, and that because I want to quantify this not for a particular measurement outcome, but generally that process. And you see that the coherent information is kind of gets an intuitive an intuitive value in this case, which is just the average of the entropy over the measurement outcomes. And now, okay, so as an exercise, it's worth calculating what happens in two cases. So, okay, so just to verify what I said before, that if I calculate the coherent information from Alice to Bob without M, not conditioned on M, I'll get 0. Actually, yeah, I'll get 0. And if I get 0 or minus 2, minus log 2. Basically, I want to calculate in this situation, IC of Alice to Bob, or R to B, without M. So try to calculate that and see what you get. And then another nice example is, let's say Bob is inadvertently also coupled to some dephaser. So to some environment, let's call it E prime. Then calculate it, and for now, let's not specify how it's coupled. So, and you can still get a result, you know, in terms of the the entropy of that environment. So you'll see that you'll get less than the maximal information in principle, and you can design very simple, specific couplings to this environment qubit so that the coherent information will be either exactly 0 or minus log 2, which is the smallest it could be, which means that basically you have no classical information and no quantum information at all. So do that as a homework. Try to design couplings between E prime and B so that you get either 0 or minus log 2 or something in between. Yes? Yeah, so it couples just to the measurement outcome, in this case, the environment. The environment is basically what makes the measurement classical. The measurement, the M system is not holding a quantum state in its hand. After the measurement is done, it basically holds a single, well, it holds a quantum state, but a definite quantum state that depends on the measurement outcome. So that's, this is a effective description of this in which I don't want to specify in advance what is the measurement outcome. I want to look at it still as a quantum channel. Just looking at it as a quantum channel and integrating out the measurement outcomes wouldn't give you the non-local effect. This is if you calculate the coherent information from R to B without M. But if I can still consider my measurements as a quantum channel, connecting an environment to them and dephasing them, as long as I include the information in this dephased part of the system as part of my information balance. Yes.
The use of the channel has the conditional entropy that's wrote there because they look identical.
Yeah, it is minus the conditional entropy. The thing is that the conditional entropy doesn't have the same clean meaning of conditional probabilities as in the case of a classical system, because the density matrix is not a probability, it's a matrix. But it's kind of conditional. Yeah, it's related to the conditional entropy. Yeah. But the conditional entropy, if you think about it as in the conditional entropy picture, then having coherent information means having negative conditional entropy, kind of negative uncertainty in a sense. That's why it's weird. Yeah.
Maybe that's how you could do that. Is there a way to think of it maybe as just think of it as a pure state, like you have R, M, and B. M makes the measurement, and now you have a,
R, M, and B without E, yeah.
no. Well, you have a,
For this, you need to for that to be a pure state, you need to specify a particular measurement outcome. Then it's a pure state.
I wanna write a pure state, which is, you know, M, if M measures, it's a superposition of M measuring some value, little m, 1, then B is a certain state, plus M measuring, you know, really writing a coherent wave function.
But this is not true. This is not what happens, right? Because M measures, when M measures, it collapses the state, right? So it's not,
Like you think of it like many world interpretation, where like I have,
oh,
I wanna think of a superposition.
yeah,
And so if I think of that superposition and now I don't include M inside the B in the coherent guy,
but,
then it's
right.
like tracing over M. And that's why I'm getting 0.
But okay, I don't know how, I mean, the only way I know how to make it into a state is by adding another kind of Q and the environment too. And this would be a many world, this is the many world interpretation. Really, it's just the many, I think of the many world interpretation as purifying this. And now we have a quantum state, but in this many world interpretation, I also have to specify what the environment is doing. Otherwise, I can't have a pure state. Otherwise, it's not correct to write it as a pure state. Only if I look at the entire system, which is pure, which is
Why can't I think of R, M, where there's superposition over outcomes of M. Entangled, you know,
because they're not in a pure state. I mean, the different because you've entangled, M has been entangled with something external to your system, so you can't do it anymore. It's not separable.
Yep. Yeah, maybe that's, yeah, exactly. Get measured, like M just M.
Oh, before measurement, but then there is no measurement outcome. Yeah, then I have. Yeah, then it's just a big wave function before measurement. Yeah, yeah. But that doesn't describe the measurement process. It doesn't even know then what basis I'm measuring in. Right. So there is no information about what I measured exactly if I just write the wave function. Right. So somehow I need to input the information that Bob can get, and that information depends on the measurement basis of M. For example, if M measured in, so here is another good exercise. Suppose M measured in a non-entangled basis. You'll see that I'll get a different result, which doesn't give me the full coherent information. Yeah. Yes, yeah, it's decided by what operators the environment of acted with, or what unitary acted between the environment and the measure. Yeah. Right. Yes. After the measurement, the pure state is R, E, M, and B. That's a pure state. Right. That's a pure state, but that's right. But now I trace out the environment and everything else and just leave myself with, right. E and B are not in a product state. E and M. E and M, E and B are not, well, no, they're not, because for different measurement outcomes, right, I'll get different. Yeah. After I measure it in a different state, definite state, but now I'm looking at this as a probability mixture. There is a probability PM that it went into this definite state, a probability. So that basically that's what defines the BM system. Yeah. Yeah, yeah, absolutely. That's right. Yeah, yeah, yeah. Yeah. So the purpose of the measurements is just that without the measurement, I will not create this non-local correlation, right? Or the purpose of the measurement is that with the knowledge of the outcomes, I can actually reconstruct, I mean, information theoretic measure, meaning is that with the if I do the proper measurement, there is a non-local correlation created. And what it means is that I can now use the information about the measurement outcomes to apply some unitary and create the state Alice had in my, without knowing in advance what it is, to recreate it in my lab. Okay, so the idea of teleportation is that once I know that knowing the measurement outcome gives me enough information to reconstruct Alice's state, although I didn't know what it is in advance. And the information theoretic object that checks whether I do have enough to, what is the teleportation fidelity in a sense, what is, how much information I can teleport, is this coherent information. Yeah, Alice is inputting a state into here, right? But whenever I input a state, I can think about it as instead as a larger dimensional single ket Hilbert space. Yeah, and I don't care in this case. I don't specify what is the state because I'm computing the information independent of what that state is, right? So I don't care what the state was. It basically is just the maximal information I can transmit. Yes? Yeah, yeah. No, it's not quantum system because M system has only classical information because it has been totally dephased. The density matrix of the M system is just a completely classical diagonal density matrix with the probabilities PM for every outcome. So M system does not contain in itself any quantum information. Okay, so it's basically what this tells me is that if I send the information in M to B, which is completely classical information, that would be enough. Together, M and B have quantum information, but M itself has only classical information. Yeah. So this is for kind of this well-known teleportation of protocol with two parties and so on. And what I want to show you now that it's very, very similar. I can think of the entire measurement-induced transition in quantum circuits in exactly the same terms. I won't have to do almost any modifications now. But the nice thing is that because it's a very interesting many-body system, it would be interesting to see how this that particular object can undergo a phase transition in this case. And you can see that it undergoes a phase transition by translating this information theoretic object into statistical mechanics, physical observable in the StatMech model. Okay, so let me now turn to the MIP measurement-induced phase transition in random circuits. I won't give you an introduction because I guess Romain talked about it already, but maybe the minimal necessary. Leave that. Yeah, okay. I can erase this. So hopefully people there can see. I'll give a kind of lightning fast reminder of the StatMech model and what it means for the measurement-induced transition. So before a StatMech model, just a reminder. So in the measurement-induced transition, we have, let's say a brick wall. It doesn't matter so much, but the brick wall circuit of unitaries. I'm a little bit lazy in drawing everything here. Maybe all the legs you should, in your imagination. Okay, this is the brick wall circuit, and there are some measurements that maybe I'll use red color measurements at some locations, somewhere here, and there is an input state and an output state. Now let's look at the let's look at what is the equivalent circuit. Can we write down a circuit like we did for this system? Well, we can. So this is the unitary. There is the input state. I can always write down as a reference qubit in a larger dimensional Hilbert space, and I can and the measurements. So measurements, these points, this is the measurement system M. Okay, and I can connect it if I want to an ancilla, to an environment that purifies it. Okay, so physically, if you want each measurement, I have a small, first of all, I have one small ancilla that basically is unitarily coupled to my physical qubits. And actually, I measure that ancilla in place of my physical qubits, which stay kind of continue. And measuring means I need to connect that system to another ancilla that dephases it, just like before, right? So we have the M system, the Bob system, which is the output, and the Alice's system, or reference qubit, just like before. And now we can ask, what is the coherent information from R, just like before, to B and M. And again, we can get non-local effects and all the interesting effects of the measurement-induced transition only if we calculate this, and not if we calculate this, then the measurements are essentially like just like decoherence. And we won't get any kind of interesting non-local effects in this case. So we need to condition on the measurement outcomes, although they're just, and now we don't have to do the exercise again because it's exactly the same as what we had there. This is exactly equal to the average over measurement outcomes. Average over measurement outcomes of the entropy of B. So in this situation, because I have I'm maximally entangled the input with some reference, note that I have a maximally mixed B. Initially had entropy log n times log 2, where n is the number of qubits. So there is maximal, and you can ask whether it purifies or not. And if that averaged over measurement outcomes, if it purifies, you have one phase. If it doesn't purify, that's another phase. So at least that's a well-defined question. I didn't show you that this is exactly the same transition as the transition that you have in the subsystem entanglement entropy, and we'll see that in a minute. But as long as we're talking about, yeah?
B and M are?
Yeah, so the dotted line between B and M are basically for example, a control Z gate, for example, that basically that is applied. M is an ancilla that has a gate and has a control Z gate between it and the system ancilla. And then I measure, I apply it for pi over 2 and measure the ancilla. And that basically gives me a measurement of the system qubit. So that's a way to physically implement that dotted line. It's just a unitary gate. What? Oh, E is doing, because if I don't have E and I apply this gate, then M is holding a quantum state in its hand, okay? And that's fine, but it's not the it's not the picture in the measurement-induced phase transition. In the measurement-induced phase transition, we basically collapse the state, or in other words, we have to get M becomes holds a it doesn't hold a quantum state, but is in a probabilistic mixture of the different measurement outcomes. And to make it in a probabilistic mixture of the different measurement outcomes, I connect each ancilla in M to another ancilla that does this controlled X gate that dephases it. All of these are just tricks. I mean, the gates you apply are not so important. It's just kind of neat ways to get into the state that you want, where M is in the density matrix, diagonal density matrix with the probabilities of the different measurement outcomes on the diagonal in the measurement basis. So we need E in order to get M into that classical state. Otherwise, M is holding a quantum state in its hand. It doesn't. Exactly. M is in the measurement apparatus. Before you dephase it, it's just in the quantum state itself. E is in some sense measuring M, right? Right. But you need that in order to think of M as a classical measurement apparatus. Yeah, yeah. Right, right. Oh, exactly the same thing. What it does in this situation, in that case, it serves so that M will be in a diagonal density matrix, basically in a mixture of possible states. If you measure M1 in the Bell basis in this case, right? So the coupling to E is designed in such a way that that M will be in a classical probability mixture, that it has probability P1 to measure Bell pair 1. It has probability P2 to measure Bell pair 2, and so on. So E is made to put you in that state, and that specific operator I gave is just an implementation that does that most easily. But then
you condition on your measurement outcome you want to do something.
Yeah.
Cover the state.
Right. So yeah. So what you have to here, the conditioning on measurement outcome is in the sense that I'm thinking of the coherent information not from R to B, but from R to the entire system of B and M. That's how I take the measurement information into account. If I don't have it, it's like integrating out. It's like tracing over the measurement outcomes, and then it's basically a different problem where I'm discarding measurement outcomes. I basically have only a quantum channel acting on my system.
So just if there is a usual measurement based on have your measurement, you apply C, you initialize all the M ancillars,
Yeah.
apply C.
Yes.
At the final time, are you going to make measurements with your M?
Yeah. Yeah. Physically, you have to make measurements, and you have to remember the measurement outcomes somehow and use them, right? So you have to make measurements. So another way to answer also another question that you asked is, what's the role of E? If I only had E, it's like the environment also measures, but environment is something that I'm always discarding. Okay, so if I have just E, I'll discard E, and there will not be any kind of non-local effects on measurements. But if I don't regard my measurement apparatus as an environment, it's part of the system, I can include it in my information balance, then I need another environment in order to completely purify the system. Yeah, I need B is B is not in a pure state. It's in a pure state only for each, if you want, for each measurement outcome, for each trajectory, it's in a pure state, but not for in that picture, it's not in a pure state. It's in a pure state only if you consider trajectories, if you unravel this picture into different trajectories. But this is the non-unraveled picture. It's not unraveled, and in this case, it's not in a pure state, right? Yeah, I'm viewing it, I can still view it as a channel, but then I have to be careful. Viewing it as a channel is totally correct, but I have to, and it's very useful, but then I have to make sure that M is not an environment. It's not something I trace over. It's something that I include in the information balance. This is basically everything conditioned on the information conditioned, and you see that, when I calculate this object, it indeed gives me what intuitively I want, which is the average over the different measurement outcomes. This is the unraveling of this, unraveling into trajectories. It's average over the different trajectories of the entropy I have in B for every trajectory. That's right.
There's one thing that's always confusing me, but if I wanted to input a state of wave function.
Yeah.
How do I input that with R? Is that?
Yeah, I think that. Yeah. So that's right. So here I'm not inputting an actual state because I'm asking about the general. Yeah, in a sense, it's a maximally mixed initial state. Yes. Right. It's
If you actually had people that are being really teleport.
Yeah. I can in fact I can enter with, think of this as inputting a state. Then to recover what I calculated now is what is my capacity to recover any unknown state. The fact that my state is unknown is basically described by the fact that if my state is known, I could, apply the unitary I want to recreate. But the fact that I have a maximally mixed state with this R basically tells me that I could, in principle, input any state, and I want to quantify my ability to teleport. If it was a particular state, we just don't tell what it is to Bob. It's enough for Bob to get the measurement outcome to construct the correct decoder, although he doesn't know what that state was. But yeah, this way of writing it doesn't give me an access to input a particular state. In principle, I could do that by putting basically closing that with a particular basis state here, and that would be inputting a particular state. Yeah.
Why can't R be just a specific state?
Well, because here R is still an open index. I didn't specify anything, right? It's just an open index, so it could have anything. Like in matrix product states, if I have open legs, it's not a specific state. It could be anything, right? To have a specific state in it, you need to input here. You need to, in this drawing it, you'll have to contract it with the state that is with a bra state, right? And this bra state is coming from here. Yeah, this is the Choi representation. That's right. So to have a specific state coming in, single qubit state, because that's what Alice can input, just a single qubit state, you need to close that with a particular, but here I don't want to do it because I want to specify the general capacity to go through this channel. Yeah.
And just to follow up on the previous question.
Yeah.
If you didn't have, just to be clear, like if you didn't have this, and you just wrote down this. See, we just always do zero are greater than.
Sorry, if I wrote.
If there was no environment, like there was no actual.
Yeah, then it's a pure state of, then we have a pure state.
Of R.
RMB. Yeah.
Well, and then you compute
Uh,
the IC that you have written down. Would it be
From,
zero? That'd be nice.
yeah, maximum. Yeah. From R to M and B. It will be maximal because R, but not because of B, but because everything is in M. Yeah. Because R and M are maximally entangled, but this would be unsurprising because everything is kind of, everything is in M. When you do dephase it, you basically destroy the quantum information in M. There is only some classical information left. And nonetheless, you can reconstruct it in B. Yeah. Okay, so now one more information, interesting information, theoretic quantity is, let's ask a different question. We have the same circuit, and M is, we can call M Eve. M is Eve. It's someone that eavesdropped on this. So I said that Alice is trying to transmit information to Bob, and I asked whether she can transmit information to Bob. You can ask the other side of the question, whether M alone can decipher some of this information. Now, M is classical, so she can only decipher kind of a classical part of the information because she measures in one particular basis. So we can ask how much of the classical information contained in Alice's state they can, M can, or Eve can reconstruct. And to do that, we can do very similar, we can look at a similar situation where instead of, only having an environment E, I can also dephase R to make it classical. So the R part, I'm also making only classical. So let's call it E prime that dephases, and the same, have some control X gate in the basis. I want R some natural basis for state R. And now I can ask how much classical information do R and M share? So how much can I learn about the state of M if I know the measurement outcomes? So this would be I of R and M in this particular circuit where I dephase R and M, which is basically S of R plus S of M. Let me write it, S of M plus S of R minus S of Rm. And we can also rewrite it as Sm minus conditional. So this is minus this coherent. This looks like conditional entropy, right? And we already calculated this kind of thing because remember that is in a diagonal density matrix with only the probabilities PR. So we can do the same trick as before. Now you can look at it and convince yourself that it's basically sum over R, PR times S of M given R. So this part is what we have here. And this will come useful in a second when we look at the StatMech model. Yes? Sorry. It's the same setting as before. M equals what?
Why you said M is E?
I didn't say M is E. Rho M equals rho E. What? Eve. M, I just call M Eve. Sorry, it's M. Now M is an Eve. I want to have a different interpretation of the same measurement-induced transition circuit again. So this is not an equation, it was just a naming. So now it's just natural to ask before we ask the question, Alice is trying to transmit some information to Bob through this circuit, and someone is making measurements. And then the question was whether, with knowledge of the measurement outcomes, we can reconstruct the initial state, the initial quantum state. Okay, that was the initial question. Now I'm asking kind of a related question that's the other side of the coin. Let's say now, not from the perspective of Bob, let's look at the perspective of the person making measurement, which I call Eve. Whether Eve can reconstruct just from the measurement outcomes the initial state of Alice. Yes.
And there's no connection to E, right?
No, sorry. Actually, M is also good. Like, you know, in James Bond movies, M is also at the head of the MI6, and probably this is, maybe we should say Bond is trying to get something from Alice, and M wants to check if they're not flirting. Sorry for making this confusion, but forget about Eve. It's just I was trying to stick to quantum information culture, which I'm not part of, so I'm not sure yeah, so anyways, but so forget about Eve. M is trying to measure, is measuring, and the question is, how much of Alice's initial state can M reconstruct just based on her classical measurement outcomes, not with Bob's system? And this is in some, you have a question there? Yeah. Yeah. So in principle, I don't even have to do it. I did it because you will see that it first of all, because it can't do it, but also it will make it much easier to map, to understand the mapping to the StatMech model when I do it. And here I dephase R because I don't have any chance of reconstructing a quantum state just from having classical measurements in hand and not holding any quantum state at all. Yeah, so yeah, maybe this is a little bit shady what I did, but I did it kind of for my own convenience. It still makes sense as an information question, how much I can reconstruct. And it turns out to map to a very different quantity, and that's why I want to also look at that quantity in the StatMech model. Yeah. Between M and E, there is a CX gate. Yeah, and M is really representing many ancillas, and there is a CX gate individually between each one. Because I'm making many measurements, let's say each one is different ancilla, so you have many CX gates. And R could be whatever you want. Here, let's say R, in this situation, the most interesting case that I look about it is R is a single qubit, and all the other qubits are known. So for example, I start with some well-defined state 0. And I want to know only one qubit. I'm sending one qubit, and at least there is a classical part of this qubit that I maybe am able to learn. And the question is how well I'm able to learn it. And one way to quantify it is through this mutual information between R and M. And that will, yeah. So I see that my time is almost up. I went through like 1/4 of my lecture, but what? Yeah. That's the rune, you know. Yeah. Okay. So do I have maybe 10 minutes just to that part would be 5 minutes. Okay, I'll try with 5. Okay. So what I want to do is just to remind you about the StatMech model and ask how these measures translate to the StatMech model from what we know about it. So I want to remind you. Should be fresh in your mind The StatMech model, we want information quantities. Information quantities are calculated from multiple copies of the density matrix. If you want to, and you have to, no choice, but in the end to take some limit, replica limit. So Roman talked about it. You talked about it, right? So, and just as, so you want to calculate evolution of the density matrix. Row multiple copies. So simplest example is, let's say 2 copies of the density matrix is simplest to draw also. Basically, I start with, say, some state. As an example, I start with a pure state psi naught. So this is the density matrix. If I want to calculate the purity, for example, I just need 2 copies of the density matrix. Let's say purity of subsystem A subsystem. I need two copies of the density matrix. And 2 copies of the density matrix are evolved by 4 unitaries, right? 1 unitary for the ket, 1 for the bra, 1 for the second ket, 1 for the second bra. So it's U star, U star. But this is not only unitary evolution. If it was only unitary evolution, then and in the end, I need to trace out the B subsystem. So I trace out because remember, there are lines sticking out. Tracing out means summing over indices. And I can write it like this. This is copy 1, I trace out B. This is copy 1, I trace out the B subsystem. And then I have remaining open legs, which means the reduced density matrix of A and the second copy of the reduced density matrix of A. Now I need to multiply them one by another. So I then, multiply this index by this index. That multiplies them. And now I need to trace. So I need to trace. These are the remaining indices. So this is the entire thing I need to calculate. This thing is very complicated to calculate. Remember, I didn't draw it, but there are many, many unitaries here. In each one of the copies, each unitary evolution is made out of many, many unitaries. It's a very big many-body time evolution. That's, of course, very, very hard to calculate. It's basically a many-body path integral with summing over all the paths of the first circuit, first copy of the circuit, the second copy of the circuit independently, third copy of the circuit. They're all independent summation over these paths. They're independent except for the boundary conditions that connect them without measurements. When I have measurement, this path integral, this big path integral now does have connection between the different copies, because every time I make a measurement, I lock all the copies at that particular site to have exactly the same value, right? So you should imagine now pinching measurements, pinching them, all the copies to have exactly the same, constraining them to have exactly the same value wherever I have a measurement. I don't know how to draw it, sorry. So yeah, you'll have to kind of pinch it in your head. So this is what we need to calculate. Seems pretty complicated, and I think what Roman showed you is that it gets simplified by a lot if we average over the unitary, the Haar random unitary. So in each unitary inside this big circuit, each unitary like that has 4 of them. And if we average over them, it's averaging over UU star, UU star. So before averaging, what I do is this UU star is unitary operator in a Hilbert space, which has, instead of a qubit per site, it has 4 qubits per site. So it's a 16-dimensional Hilbert space, or but after averaging, this operator, it turns out that the averaging is a projection onto a lower dimensional Hilbert space with only 2 states per site, from 16 down to 2. And the only states that are left are the states that correspond to pairings between, so the only states that are left are states, let's term them as sigma and tau. There are states that label permutation between the copies. And in the case of two copies, there could be only a permutation, identity permutation, where I have, so the two, I said I projected to two states. I can explicitly write down these states. So the two states that remain in my Hilbert space are the identity state, which is sum over alpha and beta, alpha, alpha, and this is copy 1 times beta, beta. This is copy 2, which in another way of writing them, it's just, geometrically, it's written, it can be written like this. I identify the indices of the ket and the bra in copy 1, and the indices of ket and bra in copy 2. Or another way to see it, you can see it here. This is ket and bra in copy 1, ket and bra, let's call it alpha bar. Because they originate from ket and bra. So this is a state that remains. And the other state for the two copy Hilbert space is the swap, which is same alpha beta sum. And we'll call this one plus state. This is a plus state, and this is, say, a minus state. Okay, so there are two states remaining only. They're not orthogonal states, but these are their basis. These are the two remaining states up to normalization. And now we can think of this unitary evolution as instead of a unitary evolution, what we get is a transfer matrix in this two-dimensional local Hilbert space. And we can think of this transfer matrix as it's a transfer matrix in 1 + 1 dimension. And you can think about it as a stat-mech model, as a partition function in a two-dimensional system in this case, the D + 1 dimensional system. And it turns out because there are two states, and the interactions between them, the partition function has an action with ferromagnetic interactions between them. It's a ferromagnetic model. If I had more copies, I would get more states. In fact, I'll have it will be like classical spins with n factorial that can take n factorial number of labels of states. So there'll be these permutation spins, and instead of an Ising symmetry, I'll have a permutation symmetry, global permutation symmetry. So it'll be a ferromagnetic model in this permutation space. Okay. Yeah. Okay. So let's yeah. So I'll continue next time. So the next time I'll basically show how these information measures are expressed in terms of the stat-mech model.